We have seen how a particular load impedance, when we want to obtain its admittance, we have to go to a point that is diametrically opposite in the Smith chart to obtain its admittance. For example, in this situation, we see a certain load impedance of 0.6 plus j 1.2, the normalized impedance. To obtain its admittance, we go to a diametrically opposite point and read the reactance, the imaginary part and the real part from the constant resistance circle and the imaginary part from the constant reactance circle to obtain its admittance. So, to obtain admittance each time, to flip it over by 180 degree is going to be a cumbersome process. Now that we know that any impedance point, we go for a diametrically opposite point to obtain its admittance, wouldn't it be easier if we map for every impedance point on the same chart, we are able to overlay another chart to obtain at that physical location both the impedance value and the admittance value. Turns out that that is possible, and that would be very helpful for maximum power transfer and impedance matching purposes. Such a chart is called as an admittance chart, which looks like this, where for every impedance point, the diametrically opposite point, we get a certain real part and an imaginary part. That real part and imaginary part is traced back to the same physical location as the impedance point that was in the original impedance chart. Meaning, let's take this real here. The corresponding same physical location in the admittance chart is still the same, but then it has two different set of curves unlike the impedance chart. By traversing through those two set of curves, we can obtain the admittance of that particular load impedance, the conductance and the susceptance for that particular admittance can be read from that chart. Turns out that to obtain the diametrically opposite point, all we need to do that to obtain the new chart is to flip over this chart upside down and right side left. We need to have this twofold symmetry to obtain the admittance chart. So every full circle, the constant resistance circle that you see here in the impedance chart is on the right hand side of the chart, maps to the corresponding constant conductance circle onto the admittance chart to the left side of the admittance chart. Similarly, the constant reactance curves that you see in the impedance chart is going to be mapped from the right to the left, is going to be mapped from the left to the right in the admittance chart. So in the admittance chart, we have very similar to the impedance chart, two sets of curves, and those are called as the constant susceptance curves, which are the segments that start from the left to a point on the rim of the Smith chart, and a constant conductance curve, which is very similar to the constant resistance curve, but it is on the left side of the Smith chart. It's a full circle. By including these two set of curves for any given point, which is the same physical location in the impedance chart as well as in the admittance chart, we can obtain the conductance of that particular admittance as well as the susceptance of that particular admittance. It is important to note that on the rim of the Smith chart, the values that are given are the negative of the susceptance. Instead of giving negative values here, what you read from the Smith chart is going to be the negative of the susceptance. For example, in this case, for this particular load impedance, the susceptance BL is negative 0.667, but what you read from the chart is 0.667. What you read is negative of the susceptance. We know that the upper half of the impedance chart is reactive, is inductive, having positive reactance, and the lower half is negative reactance, meaning it's capacitive in nature. Then correspondingly, in the admittance chart, the upper half is going to be negative susceptance and the lower half is going to be the positive susceptance. So still the upper half region is inductive and the lower half region is capacitive. Remember, an inductor has positive reactance and hence negative susceptance. A capacitive has negative reactance and hence positive susceptance. So thus we can see that by going through a constant conductance curve and a constant susceptance curve, we can read the conductance and the negative of the susceptance to obtain a particular admittance for a given impedance from the admittance chart.